All right, the next concept we're going to look at is the collection of a gas over water. This is simply a good explanation of Dalton's law of partial pressure. And what's kind of fun is you're going to get to do this in lab. So this is a lab called the molar mass of butane. And so what you do is you basically are holding a lighter under water for a very, very long period of time, weighing the lighter before, weighing the lighter after, seeing what happens, and then trying to calculate what the molar mass of butane is by collecting the gas vapor over water. But what makes these questions interesting is that above the water, you're not just collecting the butane, if you will. You also have some water vapor that's going to be over the liquid. So look back at this. Anytime you have a gas that's released, like in this case, where it's released and then pushed through and allowed to bubble up through a liquid, which is a great way to collect a gas, you've got not only the gas of interest here, but you also have some water. And so whatever water you've got inside this container naturally has little water vapors that get released. Basically water that is going to overcome that surface tension and going to turn into a vapor above here. So the pressure that is exerted here, or all of the liquid, that the gas that's collected over the water, is not simply due to whatever your reaction is inside of your vessel, it's also due to water vapor, which means whatever your pressure total is, it's due to your pressure of your gas of your interest, so molar mass of butane, it'd be due to butane, but it's also due to water. And so whenever we're doing these calculations, they become Dalton's law of partial pressure problems that are very specific. And so what it is, it's what is the total pressure? Often this is like atmospheric pressure. What's the pressure of water at that pressure? And then what is your gas of interest pressure? And so you can learn a lot simply by doing these types of problems. But what they rely upon are Dalton's law of partial pressures and your ideal gas law, pressure times volume equals moles times gas law, gas constant times temperature. But then also that third thing is remembering all that stuff you know about converting from grams to moles and vice versa. So let's try our first problem. Zinc metal is added to hydrochloric acid to generate hydrogen gas, which is collected over a liquid whose vapor pressure is the same as pure water at 20 degrees Celsius, which is 18 torr. The volume of the gas mixture is 1.7 liters, and its total pressure is 0.180 atm. Determine the partial pressure of the hydrogen gas in this mixture. Okay, so what have we got here? Let's identify some variables. First off, the most obvious variable is this one. Total pressure. That spelled it out pretty well for you. Okay, so that's total pressure. And then it says it's collected over a liquid whose vapor pressure is the same as pure water at this temperature. And so what you've got here is some kind of pressure that you could use in this equation. And in this case, our gas of interest is our hydrogen, and we can use this pressure in here in place of water. So instead of collecting it over water, we collected it over some other random liquid. Doesn't matter. The vapor pressure is the same idea. You still will have whatever that other random liquid is will be turned into a vapor above the liquid. And so what we first have to do is, you might think, wow, that's easy. Just take the total and subtract this pressure here of the other liquid, and you'll end up with this. One small problem, though. I hope you notice what's different about these two pressures. Any guesses now that I'm underlining it like crazy? Yeah, they have to be in the same unit. So we need to convert our 18 torr to atmospheres. And so if you look back at some of your old sheets, you'll see that we can convert 1 atmosphere to torr by using 760 torr is equal to 1 atmosphere. And so if we do this, this is the same as 0.2367 atmospheres. And so this is the pressure of the other liquid, or where we're plugging it in here. And now that we've done it, it's a pretty simple problem. We have our total pressure, 0.810 atmospheres, equals the pressure of hydrogen plus the pressure of the other liquid, which in this case is 0.02367 atmospheres. And so now if we take 0.810 and subtract this 0.0237 number, you're going to get a partial pressure of your hydrogen equal to 0.786 atmospheres. And remember, your sig figs for adding and subtracting are best based on place values or number of decimals. And so this is one way that we can do this calculation for collection of a gas over water. This is about as simple as it gets. So let's try another one that's much harder. Oxygen gas, which is generated by this reaction, is collected over water at 27 degrees Celsius in a 2.58 liter vessel at a total pressure of 1 atmosphere. The vapor pressure of water at this temperature is 260 torr. So, how many moles of potassium chlorate were consumed in the reaction? All right, there's a lot going on here, but you know how to do all of it. I have faith in you, okay? But first off, let's do some figuring out and getting things into the right unit. So you might have noticed that we've got torr up here and atmospheres over here. So let's start out the same way we did the last one. Let's remember that P total equals our pressure. In this case, this is our only gas, okay? So, and that's what we said was collected. So pressure of oxygen gas over water. And so that's how we're going to use this equation. So total pressure equals the pressure of oxygen plus the pressure of water. We know our total pressure, which is this, pressure total. And we also know this, which is our pressure of our H2O. But like before, we need to convert torr into atmospheres. So let me do this over here. 1.00 atmospheres equals your pressure of your oxygen plus my pressure of my water, which is 26.0 torr. But that's not good enough. You got to convert it. So 1 atmosphere is equal to 760 torr. You can do this before the problem or you can do it within the step, whichever one is easiest for you. But now if you do this math, you're going to get pressure of oxygen equal to 0.966 atmospheres. But is that all I'm supposed to figure out? No. I'm supposed to figure out how many moles of this were consumed. Is this directly related to this number? No, but I do know that pressure of oxygen is related somehow to my moles of my oxygen. And so if I can figure out how many moles of oxygen is produced, then I can go from moles of oxygen to moles of potassium chlorate to grams of potassium chlorate. Or in this case, we can stop right there because it asks for moles. So if we do this, how are we going to get from pressures to moles? I hope you realize that PV equals nRT. But do we have enough information? Let's see. Pressure is 0.966 atmospheres. Volume is 2.58 liters. Equals moles, which is what I'm trying to find, times my gas constant, 8206, and that's liters times atmospheres per mole K, times my temperature, which is 27 degrees Celsius, but you can't leave that in Celsius, you know that. So it is 300.15 Kelvin. And if you do all of this, now you can solve for the moles of oxygen equals 0.101 moles. Now the thing with this, nothing is appreciably tricky, but I'm well aware that sometimes it's a good question to ask is, how do I know what equation I'm using? And so you have to look at your stuff, look at what equations you're given, and look at what variables you're given, and then think about what you know and how you can use it to create what you don't know. All right, we're not there yet, but we're almost there. Now I need to convert moles of oxygen into moles of potassium chlorate. So how do I do that? My balanced chemical equation, of course. So 3 moles of oxygen for every 2 moles of potassium chlorate. And that gives us a final answer of 0.0675. And there is our final answer. And so with this, we'd use two things. We used Dalton's law, and then we also used the ideal gas law. And then if you really want to think about it, we used stoichiometry, which is simply balanced chemical equation mathematics. Let's do one more. Here is our last Dalton's law of partial pressures and collection of gas over water problem. So we have 193 milliliters of oxygen collected over on water on a day when the atmospheric pressure was 762 millimeters of mercury. The temperature of the water was 23 degrees Celsius, and that is the pressure there. How many grams of oxygen were collected? So in this case, we're collecting oxygen. That's what we know. We also know the atmospheric pressure, which is 722. So this is P total. We also know our pressure of water. So all that's left is, what is my pressure of my gas of interest? That's what I'm wanting to know. So how would I do this? Well, you remember that pressure total equals pressure of my gas of interest plus my pressure of my water. And so the only thing I'm going to have to do is convert these to millimeters of mercury to atmospheres. And the reason I want to do that is because I know, and you could do it at this step and then we can convert it later. So either we can convert both of these to atmospheres, or we can plug these in and then convert the final pressure. And then we can convert the final pressure if we'd rather do it that way. So meaning we can plug each of these directly in and then get PO2 and then convert that to atmospheres, or we can convert these to atmospheres first. Why do we have to convert them though? And the reason for that is in our ideal gas law, which we're going to be using in a second, our gas constant is 0.08206, and that's liters times atmospheres per mole K. Since that gas constant has atmospheres in it, we also need to use atmospheres. So let's plug these in and go ahead and solve for the partial pressure of oxygen. So I'm going to do pressure total 762 millimeters of mercury equals pressure of my oxygen, which we are solving for, plus the pressure of water, which is 21.1 millimeters of mercury. And now that we've done that, we can solve for our total pressure of oxygen, which is equal to 740.9. And notice that this is my last sig fig right here. And that is millimeters of mercury. So then I need to convert that. So how do I do that again? 740.9 millimeters of mercury times 760 millimeters of mercury are equal to 1 atmosphere. Okay. 1 torr is the same thing as millimeters of mercury, and so you might notice it's the same thing. So we end up with 0.97487. And that 4 is my last significant digit. Sometimes I'll underline it just to remind myself, and I end up with atmospheres. All right, so where do I go from here? Let me switch colors. Next, we want to use the ideal gas law, PV equals nRT. So what's my pressure? I just solved it, and this is my pressures of oxygen. So think about each of these things relating directly to oxygen. 0.97487 atmospheres. Times my volume. Do I know my volume? Look up there, see if you can find it somewhere. Good. I hope you found it. Way up here at the top, 193. Oh, but wait. Do we want to use 193? We sure do not. So we want to use 0.193 liters equals moles. Do we know it? Nope. We're trying to solve for grams. So we're going to solve for moles, and then we'll convert that to grams. So then my R is 0.08206 liters times atmospheres per mole Kelvin. And then my temperature, do I know it? Can I just type in 23 degrees in there? No, you can't. So 23 plus 273.15 is 296.15 Kelvin. And now we can solve this for moles. And now we can solve this for moles. All right, now if we want to get to grams, how do we do that? And notice this is O2. That's important because now when we convert from grams to moles, we know 1 mole of O2 does not have a mass of 15.999. It has a mass of 31.998 grams to give us a total number of grams equal to 0.248 grams of oxygen for a final answer.